Good morning, everybody, or good afternoon in Australia, good evening. And this is Peter Murphy and Danny Carney here in Xtratherm in Ireland. So I hope that you can hear us okay and hopefully see us okay as well. As I sent the invitation over to you, you can see that we're broadcasting on Google Plus via Hangout on Air and also through YouTube. So you have the links, so if there's any problem through Google Plus, you can get the link on YouTube. So this is the first in a series of what we hope will be a series of webinars to broadcast some useful industry updates and technology updates to technical personnel in CSR Bradford from Xtratherm. So the first theme we thought would be of interest is one that's come up is the area of thermal bridging, which is an important topic for us here, and it's becoming more and more important in Australia from what we can see. So Danny, who is head of technical services, has put together a presentation for you, which is based on material you would normally give in terms of talking about the whole topic. So I'm going to hand over to Danny now. His presentation will probably take between 20 minutes and half an hour. So we'd invite people to interact with us via the chat, or if you can interact directly to ask questions during the webinar. So I'll hand over to Danny now, and we'll cross over to his PowerPoint presentation.
Before we go on, can we confirm that there's anyone actually listening to us?
Yeah, I don't know if on the audio, can anybody interact directly with us on the audio side of things? Okay.
Perhaps you can send an email to say that you're there.
I know if you're on YouTube, which some of you are, you wouldn't be able to communicate with us. You can just hear the broadcast. So yeah, that wouldn't. So it won't show up there. So I think go ahead. It'll be. This is all recorded on YouTube anyway, so we can give the link afterwards to the broadcast if anyone has trouble getting in. So I think
this is my most personal piece of education you've ever received, Peter. It's very cozy. Good morning, everyone. And it's nice to speak to the new guys amongst you. I have met a couple of Malcolm and a couple of guys previously in Ireland here, and I know that the technical issues are becoming more prevalent in Australia. So we know that the building regulations in Europe are a good bit advanced in Australia. But I've said to the guys previously, whatever has happened in Europe, it will become in your direction, because building fabric and building conservation and insulation always follows the same paths. It's the same principles that are followed. U values, R tightness, thermal bridging. So what we've experienced here, it will become in your direction. One of the things that is really hot and heavy at the moment is thermal bridging. So I'll begin the presentation now.
Okay, so we just switched over.
Okay, I've titled the presentation Envelope Performance and the role of thermal bridging within that. We know that fabric performance, whether you're going for passive house, you're going for building regulations, fabric performance is now seen as the most important factor when it comes to low energy or near zero carbon buildings. The building regulations in the UK, throughout the European member states, and for organizations such as Passive House, it's all about the conservation of energy. No matter where you're getting your energy from, whether it's from nuclear power, oil, gas, or renewable technologies, once that energy is put into a building, the most important thing is to use as little of it as possible. The way you do this is by improving fabric. And by fabric, some reason might call it envelope, but it's basically how well the building is enveloped. So what are the tweaks we need to look at when we're building up the efficiency of a building fabric? We all know about U values or resistances. You put a piece of insulation in a wall, a floor, or roof, and you improve the resistance to heat escaping. Basically, U values in Europe at the moment, passive house levels are in Ireland here, down to U values of 0.15. Air permeability is a a principle that people seem to concentrate on. People want to build airtight houses. And the poor sister of all of them is the thermal bridging issue. And that's why I want to spend a bit of time on it. Because for insulation manufacturers, it is one area, apart from the U values, where we can give real benefit to energy performances. There are other issues, such as the thermal mass of the building. I suppose that factor for certain parts of Australia that is dependent on cooling, mechanical cooling during the summer. Thermal mass could be an important issue. The heavier the thermal mass, the more it is able to regulate extremes of temperatures. There's also external heat gain from solar and internal gains taken from building services such as ventilation systems and hot water tanks and whatever. But principally, U values, air tightness, and thermal bridging is what insulation companies are concentrating on or involved with. We know that in Australia, speaking to the guys recently, a number of our competitors have started to raise the issues. You can see here a piece made by Kingspan given into the press, and also Passive House in Australia are talking about thermal bridging quite a bit. Passive House, a more extreme method of compliance, and I don't mean extreme. Passive House is a German principle. It's a commercial organization that a lot of non-government organizations are striving to achieve, probably because national regulations are just not going fast enough. U values similar to what we're now aiming for within Europe. Air tightness, part of the principle of Passive House is to go very, very airtight, to the extent that you need mechanical ventilation to get fresh air into buildings. National regulations typically don't go that far with air tightness. But the one thing where they do concentrate on is thermal bridging, the non-repeating thermal bridging at junctions. And they put a specific value for every junction in the design. So what is a thermal bridge? Definition, a bridge is basically a gap in the insulation continuity. The heat loss at a thermal bridge is greater than in the main element that you've insulated. So if you put your 4 or 6 inches of insulation into a wall or a floor, you're not experiencing great heat loss through that. But where you have a gap, whether it's by mistake, guys just leaving a hole in the insulation, or at a junction, say between a wall and a floor, that area is not as well insulated, and they are first of all, they're a problem because you're getting heat loss, but those cold spots are now leading to difficulties when it comes to condensation. I'll explain that later on. Your types of thermal bridging, repeating thermal bridges, they're the bridges that you can foresee. They're the bridges that you know are there. So a couple of examples later on. You're insulating a timber frame construction. You know that the insulation is cut by a regular piece of timber in the form of studs or noggins. Same is the case if you're insulating between rafters on a roof. The non-repeating thermal bridges, which we are concentrating on this morning, basically occur at all the junctions within a build. So as I was saying, you insulate a wall well, you insulate a floor well. Where that wall and floor meet, it is separated by 4 inches or 100 millimeter of concrete normally that splits through the floor insulation. That is a non-repeating thermal bridge, and it's quite a significant one because it's the full perimeter of the floor. That is just one non-repeating thermal bridge. Other areas would be corners, balconies, sills, gable junctions, etc. All these are now seen as significant areas of heat loss and must be measured under regulations and under Passive House. Random are exactly what it says. The random are the splits in the insulation that just simply shouldn't occur. Meter boxes for gas metering or electrical metering that penetrate into the wall insulation would be a random. They're not measured, but they should be insulated in some way, detailed properly by the architect. So repeating thermal bridges. There I'm showing a typical timber frame. Ireland 10 years ago, we put fiberglass in between the timber studs to get down to U values of about 0.3. Then the progression to get down to 0.27. We started putting solid PIR insulation between the studs. Now, the principle that we have taken in Europe is that we will work with the component insulation materials that are most suitable in any application. So we've actually got argument approval, working along with fibre, because fibre is the natural material to put in between studs such as this, because they're never accurate, and to cut solid boards is a slow and tedious job. So you can see on the left here, the insulation the solid insulation between the studs only, and on the right hand side, the more traditional way of doing it is to keep your studs a regular thickness of 89 or 100 millimeter, fill it full of fiberglass, and then actually covering the repeating thermal bridge by a layer of solid insulation to the outside of the construction or to the inside. I think the Australian climate leads itself to follow the construction I've just shown you there, with a layer of solid board within the traditional cavity. And by doing so, by putting a thin layer of high performance insulation on the outside of the traditional stud, you get a much better performance than just filling the studs full of a good solid insulation, because that repeating bridge is there. If I show you the example of the U value calculation here, you can see I have put in PIR of 140 millimeter, fiberglass in between. And we can get down to U values of 0.31 with fibre in between. But if you go the second method and just put in a layer of 30 millimeter board on the outside of the fiberglass, you can bring that U value down to about 0.2. So a cheaper solution for the builder and a much more efficient one. Random thermal bridging and timber frame. Here you can see basically stud infills instead of insulation infills. If you look bottom right, I don't know the reason, but I think it's holding up metal beams, but there's nothing between you and the outside temperatures than just that 140 millimeter of timber. By simply putting a layer of insulation over those studs, you get quite a big benefit when it comes to the U value. There is the result of fiberglass with the layer of 30 millimeter insulation getting down to 0.22. As I'm saying, the builders would tend to go for this option because the guys that we are selling to, they're not selling timber, they're selling space, they're selling houses. And if we were able to give them the U values of such as this by keeping their timbers at a regular size, using a material that they like using, like the fiberglass, and minimalizing the expensive material on the expensive high performance material, it gives him a very cost-effective way of meeting the building regulations. Repeating thermal bridging as well, studs on a roof or rafters on a roof. You can get down to U values of 0.3 by just putting insulation in between, but regulations now state in this part of the world that you must underline all timber studs on a roof with a separate layer of insulation. And when we're calculating the U values, you know, the performance of the solid insulation, the unbroken insulation below, is a lot more efficient than that in between, because you know, putting insulation in between, it's broken every 400 or 600 millimeters by a big cold piece of timber. So you must work that proportion out when you're doing your U value calculations. All those repeating thermal bridges are accounted for when you do your U value calculation based on international standard 6946. And that is a methodology that's been developed in Europe through international standard that we all have to work to. So you first layer, you work at the insulation value through the insulation, another through the thermal bridge, the timber, and that is taken into account, and then you layer it with a single layer of insulation, and that is taken into account your working U value out. It makes a big difference. Non-repeating thermal bridges then is a very important issue now. It's an important issue because we're insulating our buildings to a very high performance at present. And the more insulation you put into a wall, a floor, or a roof, the more exposed it is leaving the gaps that is created at junctions, etc. And we've worked out that in a well-insulated house to current building regulations in Europe, about 30% of all the heat loss experienced from a property will be through non-repeating thermal bridging. If this thermal bridging is not detailed properly, it will you'll never get down to the low and zero carbon buildings that we're striving for. And more importantly, because you've insulated elsewhere so well in the build and left gaps in the construction, you're going to get problems with condensation being attracted to those cold spots. The theory being that the moisture within a building is happy enough to stay as a vapor until it moves across and hits that cold spot. The cold spot drops the temperature of the air loses the ability to hold on to the moisture, so it dumps it in the form of condensation and mold. And as we tighten up the air tightness of our house, and we put more insulation in, the prevalence of this mold is starting to manifest itself in reasonably new buildings, where people have strived for very good U values without improving the detailing. So some bad detailing in concrete build, you can see that the heat loss through the concrete lintel there over the windows. Also the sills underneath the windows. And in the large photograph to the right hand side, the thermography, you can see the floor junctions in particular, where the amount of heat loss is dramatically increased. So where is the non-repeating thermal bridges? You can see in this diagram here that you guys were busy doing U value calculations through the main body of the wall, but because we take internal measurements, the indicator here was A and B. We were working out the wall length and the floor perimeter, etc. The square C is basically ignored when it comes to the heat loss through that junction. So these junctions must now be accounted for within the energy calculation that we use to get our energy labels. This is an indication of an actual thermal bridge, and this is actually a real job that we came across in Dublin. It was about 5 years ago, and I had a phone call from a guy on a site. He wouldn't tell me who he worked for, where the site was, but he basically told me that the apartments that they were in had been built for a year and a half, and the oak floors that they'd put in had started to go black around the edges. And what the guys had done is they had actually continued the floor slab through the cavity wall insulation, so that during the cold weather, floor slab dropped in temperature, and the temperature was dropped with on the wall and on the ceiling inside the apartments. This attracted the condensation, and the mold eventually manifested itself. Now, 10 years ago, when I had only 30 or 40 millimeter of insulation in there, the temperature difference between the insulated wall and the bottom of the wall wasn't that great, so the threat wasn't there. But now we're putting in 60, 70, 80, even up to 150 millimeter of insulation in that wall. So the cold spots, in comparison, are really causing a big problem. The other thing was that in the old build, the guys would never have thought about airtightness, but now they're sealing them all up, thinking that energy efficiency is achieved by airtightness. And that is by doing that and not changing the air through ventilation efficiently will not allow the damp moisture to escape from the building, and that's why the greater threat is there. So the junction that we must measure under the building regulations now are seen in this diagram: corners, floor junctions, ceiling junctions, window heads, sills, reveals, etc. They all must be accounted for. That's what happens when you do not detail properly. You get mold growth in areas, and if you think of houses you've seen, old houses, you know where the mold is going to go. It's going to appear. It's going to be in the corners, at the floors and ceilings. It's going to be at the reveals of windows typically. So measuring thermal bridging then, every individual non-repeating thermal bridge or junction will have what's called a psi value. Psi values are basically the heat loss through any junction. So all your junctions, you have increased heat loss at them. We have a minimum target to achieve, like a minimum U value for each of the junctions now. There's also a test when you're thermal modeling to work out the surface temperature at that junction. It's called the F factor, and that minimum surface temperature is set because if you drop below that temperature, that's when condensation forms. So it must be modeled to make sure that you do not hit that target, or to ensure that you hit a minimum target. So every junction needs to be modeled if they're not modeled by a third party. And what we have in most of European states now are catalogues of standard construction details that have typical values against them. And each of these measurements for each of the junctions is it's basically signified by the psi value. You can see the symbol here on screen. The paper where we get the guidance from in Europe is called IP 106. A bit of a malfunction on my PowerPoint here. So, next slide. So that is a model. Well, a lot of people say they can model, but not very many people have actually been accredited by the authorities in the UK and Ireland to actually become thermal modelers. It is an extremely difficult scientific process to get involved with. A model like this at a wall floor junction would probably take about 3 days. So unless you're getting, in terms of euros, somewhere around 500 euros per detail, it would not pay you to do this commercially. We had, within Xtratherm here, we had the first guy qualified in the UK and subsequently the first guy qualified in Ireland to do the thermal bridge modeling, but it's not a service that we actually offer because we can't see any way of making a few quid at it. Rules for modeling based on the paper IP 106 written by Tim Ward of the BRE, and the conventions for the calculations again by the BRE, written by Tim Ward and a guy called Chris Sanders, who's now at Caledonian University in Glasgow. The default values for the junctions that I mentioned earlier on, there are separate details for Ireland because we build slightly different than England. English details here. You can see third one down, fourth one down, a window jam or a reveal will have a target for you to achieve of 0.05. If you cannot prove that, you must take the heat loss through that at 0.1. That's watts per meter K. So there's a significant advantage in actually going for the accredited values of 0.05. In Ireland, we have the same details, quite comprehensive, gutter for cavity wall, external and internal insulation, timber frame, steel frame, and hollow block construction. What you guys should be looking for to see, are there actually standard details for construction in Australia? Does any government body actually publish standard details? Because if they are standard, that's what you should be looking at to improve with your insulation products that you produce. Now, how do you get, or how are you allowed to use the accredited value of 0.05? Well, what you do is you follow the accredited details for construction that the government print for free. And each of the details here, there's about 30 details for each one of those build methods I talked about. It basically tells the guys what they should be doing on site. Double up your insulation, in this case on a ceiling, with a full layer of insulation to the underside to cover the repeating thermal bridges. At the non-repeating bridge there at the wall plate, we are ensuring that there is a thermal connection between roof and wall. That is basically it. The blue line indicated on the right-hand side is for air permeability, for air tightness. It basically says make sure you've got an air barrier in there of some sort, and that barrier can be continuous ribbons of adhesive on dry lining of plasterboard, or it could be, as we do in Northern Ireland, we wet finish our plaster, or it can be proprietary tips or whatever. So the guys make sure they follow us inside to sign it off, and I can put my 0.05 into my energy calculation. What we've done in Xtratherm is we've taken those details a step further. We've taken the details, we've put our products in, we've modeled them again, and we have improved upon the default values. So anybody buying our products immediately gets an advantage on the values at their non-repeating thermal bridge. And I have actually put this into our literature. This is, excuse me, a recently published guide to building regulations in Ireland to get down to zero carbon. And you can see the same details that we talked about earlier on: the window jambs, the heads, the sills, the ground floor junction. We can go for block type is dense, a medium, or a light. And you can see the values for the, let's take the window jamb, where the default value was 0.05. Go down to the middle of my box, the item 1.25, using a medium density block, I can bring that score down to 0.002. So a significant improvement over the default values that, by using other insulation materials, you must use. So again, the standard details, we've just taken them and put our insulation in there and had them modeled up. Now, difference in here is that we're talking so far 0.005, 0.002, 0.05. We don't use those values in the calculation for low energy build in national regulations. The difference is the passive house. When you're talking to passive house in Australia, they do. They asked for every junction in their constructions to get past a psi value of 0.01. It is extremely onerous to get this done, to meet this target. But what passive house do is they measure them slightly different. They take their measurements on a bridge from the external measurement. So again, the passive house guys will probably be pushing the regulation standards in Australia. They will be getting a voice among architects. But there is a significant difference when it comes to the national way of doing things and the passive house way of doing things. If you take passive results and you measure them conventionally to the inside, they're not that different. But I've got a bit of experience with passive house in Europe, and you know, we work quite closely with them, and again, they're just striving for a better build. There's just a bit of misunderstanding as to the performances when compared with national standards. So what we account for, how we account for the thermal bridging in national regulations is it's a Y value, and the Y value is basically the sum of all the bridges in the house. So all the non-repeating thermal bridges. So your jamb, your heads, your sills are basically quantified by length, and they're summed up, added up, and then they're divided by the total heat loss area. So the area of heat loss would be the heat loss through the walls, floors, roof, windows, and doors, etc. And that is how you work out your Y value. The way to look at a Y value is a penalty. There's a penalty for having more heat loss at those junctions. So if you're saying you were building to a passive house standard and you were able to get 0.15 of U value in the walls, in the floors, in the windows, your average would be 0.15. Now, if you add your Y value for your detailing onto that, bad detailing in Ireland is 0.15. So your average U value for the building jumps to 0.3. It's like taking half of the insulation actually out of the construction. it is a massive, massive factor. So reducing the Y value from 0.15 to 0.08, 0.08 is still 0.23. It's nowhere near what we need for zero carbon. We're getting down to values of about 0.3. In fact, the building regulations in Ireland here, you can see the left-hand column. We've got indications of the U values that we need for current building regulations, but we've also got the thermal bridging target of 0.05. UK zero carbon to the right-hand side is 0.05, and passive house 0.01, but remember that's for every individual detail. Maybe a note of interest here as well is the zero carbon standards for the UK. They've kept their air tightness at 5. Air tightness at 5 will still work with natural ventilation. They will not, national regulations will not push you so airtight that you need mechanical ventilation in. They've had experienced just too many problems with mechanical ventilation systems. So calculating the Y value out here, I've taken a typical house. And what we've done is we've quantified your window jamb. The lineal meters is 42.675. By separating the jamb out totally, we're able to get down to a figure of 0 by splitting the wall totally. Your ground floor is 74 linear meters by 0.12. You multiply all your lengths by the junction side value out. You sum them up, which is 24.37. You divide by the total heat loss area or envelope area of 791 square meters, and you get down to 0.03. 0.03, 0.04, 0.05 is very, very doable. So the Y value is a big factor. Well, I've tried to compare it here to heat loss. A Y value of 0.15 is the same, the equivalent heat loss of having a hole in the side of your house the size of a garage door. By reducing it to 0.08, you've closed that hole, not a window, not a door, you've closed the hole down to a patio door of 1.8 by 1.2. Putting good detail in, you have closed that hole down to a size of a 1.2 square meter window. So you can see people talk about air tightness. Thermal bridging is the major factor in achieving energy efficiency. There's not much we can do about air tightness, but there's a lot we can do as manufacturers to improve the detailing to achieve these Y values. So where are we in Australia with thermal bridging? It's not a big issue yet. I know some of our competitors are talking about it. It's not an issue yet because the values that we're now looking at in Australia with very thin amounts of insulation, it's not causing problems as yet if you leave a piece of insulation out. As we build the thicknesses, the issues will build. So over the next 5 to 10 years, thermal bridging will be a significant part of your building regulations. So there's some marketing advantage to be had as we did our first guide to thermal bridging in 2002. So what we talk about is best practice on site, joining the insulation properly, keeping the continuity going. And we have used the technical knowledge that we've gained to basically educate the specifiers, the energy assessors, and the builders on site about the importance of good detailing. We can give them a definite commercial advantage when they're trying to meet very, very good energy levels in the house by basically providing better SI values that almost come free because they're using our materials. We've got them certified. When you put a piece of insulation in the wall with a piece of our insulation on the floor, you get that SI value for free. So quite an advantage there. So being able to build your skills level up, get in front of architects and talk about the subject matter will help build credibility in the market. But don't let the green contingent steal your thunder. I've put here. A lot of guys will be out there shouting about thermal bridging, and they'll have half an idea of what it is. We get the same thing in Ireland, but what we're able to do is go out, get guys actually qualified to do the thermal modeling, to give them an advantage to be able to speak with credibility. And don't be frightened of it, don't run away from it, just understand it and be prepared for it. So I'd also like to investigate whether or not those standard details for all types of constructions are actually in Australia at present. And from that point, if that's what the guys actually build on site, are we able to improve the detailing at their junctions for them? And we need to develop our skills when it comes to simple calculation, like U value calculation. When I was showing you the calculation for U value of a timber frame construction in Ireland and the UK, there is a norm. The norm says that the amount of timber in that wall is 15%. Now that has come from a paper, it's BR 443. It is the rules by which we must work. And it tells you what the emissivity of fall should be taken at if it's not certified. It tells you the amount of dabs of plaster there is on the back of plasterboard when we're trying to work out the air resistance behind dot and dab plasterboard. So is there such an equivalent norm document for calculating U values out in Australia? So quite a complicated subject, but we're here to help you build your reputation as the experts in the Australian field for thermal bridging and U value calculation.
Yeah, so thanks, Danny, for that presentation. I hope all of you found it useful. I can see we have coming up on the screen, there are 5 viewers on Google Plus, and I know a number of people are looking at it on the YouTube link. Unfortunately, just with the interaction with YouTube, I know people can't interact directly with us, and I'd sent an email there that if anybody had questions for Danny's presentation, they could email them through to me, but I haven't seen anything from anybody yet. 1 or 2 other comments, Joe, I think you emailed me regarding the PowerPoint presentation, just if we could have made it bigger in PowerPoint viewer mode. We had tried that, but there's a bit of a compatibility issue with PowerPoint in viewer mode, and Google Hangouts, it freezes, and it's impossible to get back out of it once you go into it. So we have to just view it in the biggest format we could, but we try and fix that for the next one.
What we probably could do is maybe email you a copy of the presentation down anyway.
Yeah. And the actual broadcast will be available through the YouTube link, so you'll be able to look at it back, or if there are people who weren't able to participate, they can go on the link, and the re-recording of all of this will be up there that they can look at it. So yeah, we'd appreciate if you could give any feedback on the webinar in terms of how it came across, the content, and how it sounded, if there's anything we can improve. Also, if you have any other topics you would like Danny to cover, maybe in some forthcoming webinars, we could do these maybe on a regular basis, maybe once a month or something like that. Or so if you have particular issues you'd like us to cover, that you'd like more information on, please drop me an email and give us some feedback.
I'll try to soften the accent as well for the next presentation.
Yeah, so hopefully you didn't have too much trouble
understanding the Belfast accent.
So that's really it, guys. Thanks very much for participating. Send us some feedback, and hope you found it useful, and we look forward to speaking with you again soon. Okay,
Good to see you.
Thanks. Bye-bye.